Good afternoon, everybody. My name is Shangping Chang, and it's my honor to introduce my research with you. The title is Applications of Electrospun Nanofibers in Wavelength Converted, Conjugated Polymer Fibers and Fibers with Aggregation-Induced Emission Attributes. We all know that UV radiation can be harmful to humans. In fact, constant exposure to this can even lead to skin cancer. Fortunately, fibers called ultraviolet-resistant fibers can provide us with protection. UV resistance in textiles refers to a fabric's ability to resist UV radiation. The properties of a fabric, as well affect the ability of the fibers to resist UV light, include its density of weave and the color of the fiber, and also some chemical additions. However, most of the properties above simply help the fiber to absorb or to reflect the UV radiation, which is still a kind of energy that can be used. Therefore, in my research, I try to produce an effective way of changing ultraviolet light into visible light. After searching for many information, I find that Electrospun Nanofibers has many advantages that can fit my purpose. Electrospinning is a technology of polymer nanofiber producing. It uses polymer solutions as material and produces nanofibers through the balance between electrical forces and the surface tension forces. Electrospinning nanofiber has the advantages of low cost, high specific surface area, and also flexible morphology tuning. And that is why I choose it as my material and try to develop a wavelength converted ES nanofibers. The research is divided into two parts. In the first part, I try to produce light-emitting nanofibers from polyfluorens derivative and investigate the optical properties of the fibers. And in the second part, I try to produce nanofibers with another kind of method, combining PLA and luminogens with aggregation-induced emission attributes, trying to find a best wavelength converted material. First is the result of light-emitting nanofibers produced from conjugated polymer. After finding the best working conditions, I try to produce light-emitting nanofibers from the binary blend of PFO-PMMA and PFO-PFBT-PMMA. PFO is a common conjugated polymer that is often used in nanofibers producing. And PFBT is produced by applying BT radical to modify the polymer. I try to produce light-emitting nanofibers from these two kinds of polymer and investigate their optical properties. As you can see, it shows in the pictures, the fibers is not fluorescent under visible light, but under ultraviolet light, the PFO fibers can emit blue light. And after we add PFBT to a solution, the mixed fiber can emit yellow-green light. And this is because of the energy transferring between two kinds of polymer. We can investigate the properties through spectrums. First, in the emission spectrum, we can see that the two polymers has very similar absorption attributes. Both of their absorbed peak maximum approach UV light. But in the absorption spectrums of the mixed fibers, there is another minor absorbed peak maximum approach blue light. And there is where the PFBT absorbs the energy that PFO emits. In the emission spectrums, we can see the great differences between the optical properties of these two kinds of fiber. Therefore, we can make conclusions from the observations of the spectrum that the energy transferring from PFO to PFBT can change the emission colors of the light-emitting nanofibers. From the research above, we can know that we can produce light-emitting nanofibers from conjugated polymer. However, in order to increase my fibers application and to make it more eco-friendly, I tried another method to produce light-emitting nanofibers. I try to combine PLA, which is biodegradable, and luminogens with aggregation-induced emission attributes. AIE luminogens exhibit strong fluorescence in concentrated state because of their non-coplanar structure. And the luminogens I choose to use is HPS. And in this part of research, first, I investigate the effect of solvents on nanofibers while trying to find the best solvent for my fiber. In the end, I find the main factor that will influence the structures of the fibers include the solvent's boiling point and the dielectric constant. First, I try to use chloroform as my solvent, but finding unsuitable because of its low boiling point. If the solvent's boiling point is not high enough, it's easy for the solutions to solidify, which will affect the stability of spinning. Therefore, you can see in the SEM image that the fibers produced from high concentrations prescriptions is less evener than the fibers produced from low concentrations prescription. And although the fiber below is evener than the fiber above, it's still not thin enough to achieve the nanostructures that I expect to have. Therefore, in the following trials in the list, I find that I can decrease the diameters of nanofibers by adjusting the dielectric constants of the solvent. High dielectric constant provides the fiber with higher effect of the electric forces, and which can make the fibers thinner. Therefore, as you can see in the SEM figure, I can produce thin and evener nanofibers from the mixed solvents of DCM and DMF at Prosper of 7 to 3. And because of the solvent's proper boiling point and dielectric constant, I find my best solvents for my fiber. Then I further investigate the optical properties of the thin fiber, trying to find the effect of diameter on fibers. In the end, I find that the thin fibers have better fluorescent efficiencies, and also it has better applications. We can prove this attributes through the observations of spectrums. We can see that in both absorptions and emission spectrums, the thin fibers had the peak maximums of the thin fibers had redshift, which means that it has better fluorescent efficiencies. Also, the thin fibers have higher polarized ratios. High polarized ratio means that the energy that the fibers emit is more concentrated, which will make the fibers have more applications. Then, I investigate the optical properties of spin coating film and ES nanofibers, trying to find the effect of stretchings on the fibers. In the end, I find that stretchings can increase the fiber's fluorescent efficiencies. Just as what I have said, nanofibers is produced through the balance between electrical forces and the surface tension forces. Therefore, during the process of spinning, the electric field will stretch the fibers, which will affect the aggregation down inside the fibers. Therefore, in the observations of the spectrums, we can see that both absorption and emission spectrums of the fibers have redshift, which means that it has better fluorescent efficiencies. Last, I try to produce light-emitting nanofibers through another kind of AIE luminogens called TPE. And from the observations of the spectrums, I can make the conclusions that I can change the emissions colors of the light-emitting nanofibers by using another kind of AIE luminogens. And also, according to the observation of the polarized ratios, we can see that the energy that the new fiber emits still is more concentrated than usual spin coating film. So it still has better applications. In conclusion, light-emitting nanofibers can be produced either from conjugated polymer or from the combinations of PLA and aggregation aggregations, emissions, attributes, luminescence. And the emissions colors can be changed not only by applying specific radical to modify the polymers, or by using another kind of AI luminescence combined with PLA. In general comparisons, ES nanofibers has high specific specific surface area, and the effect of stretching cause ES nanofibers a great wavelength converted material. In the future, I hope that the fibers can be used for anti-UV materials, lasers, and facial masks with phototherapy. And this is the end of my presentation. Thank you for your listening.
ありがとうございました。それでは、せっかくの機会ですので、ご質問のある方、どうぞ挙手をなさってください。ご質問など、いかがでしょうか。よろしければ、高校生の皆さんもご質問、意見交換などなさっていただければと思いますが、いかがでしょうか。では、マイクをお持ちいたします。
Thank you for excellent thought. So I'd like to ask about the effects of the solvent.
Yes.
Yes, in your talk, the nature of the solvent plays a crucial role for the nature of the fibers generated. Nature of the solvent, boiling point, or some other parameters for the solvent affect so much on the nature of the produced fibers, right?
Again, please.
Yes, so for example, the boiling point of the solvent affects so much on the thickness of the fibers produced,
Yes.
right? So many high school students here are not so familiar with fiber chemistry. So could you rationalize the relationship between the boiling point of the solvent and the fiber thickness?
The boiling point of the solvent will affect the result of spinning. It's because that Electrospun nanofibers is produced by the balance between electrical forces and the surface tension forces. And it is produced by you put the solvent inside the machines, and then you add voltage to the solvent, and it will come out solvent at the end of the solvent. And if the boiling point of the solvent is not high enough, then it is sooner will the solvent become solid, and therefore it will become less even. I guess, is that okay?
ありがとうございます。その他、ご質問などございましたら、いかがでしょうか。ご質問の方はよろしいですか。はい。それでは、以上で発表の方、どうもありがとうございました。台北ファーストガールズハイスクールからシャンティ・チャンさんでした。ありがとうございました。